Dear friends, welcome to the eighth lecture of our differential geometry course. Today we will start a new section, namely section 5 point, sorry, section 5.6. The name is Special Curves in a Surface. So we will basically study three different kinds of curves. Let me start with the first one, definition. A curve a regular curve, so the derivative is never zero, in a surface M in R3 is a principal curve provided that the velocity vector alpha prime of alpha always points in a principal direction. So what does this mean? At any point on the surface, suppose you are at a point like this, and here is our let's say tangent space, okay, TPM. There are, remember, our principal directions, let's say this one, and they're orthogonal, we know that, principal directions. So our curve will be so that at any point like this one, P, a principal curve is so that at this point it will be tangent one of the two principal directions. Okay, so this is our alpha, and say these are our principal directions, E1 and E2. Let's say E1 and E2, and it will be always parallel to one of the principal directions at any point. Okay, so that's the definition of a principal curve. Okay, so here, of course, maybe I should remark a few things. Principal curves moves in directions in which the surface bends the most. Maybe I should say the most in extreme values, because principal directions are exactly those directions. Therefore, principal curves always moves in those directions in which the surface bends either the most or the least. Okay, of course, through an oblique point, every direction is principal. So at such a point, you know, any direction is principal. Okay, but usually there are only two such directions, right? At any point there are only two such directions. So at any point there can be at most two principal curves. So through an non-umbilic point, there passes exactly two principal curves. Okay, one of them is this alpha, and there can be another one. All right. Okay. Here is a lemma. Let alpha be a regular curve in M, and let U be a unit normal field along alpha. Then the conclusion is, there are two conclusions. First one is the curve alpha is principal if and only if U prime and alpha prime are collinear at each point. The second one, if alpha is a principal curve, then there's then the principal curvature along alpha prime is alpha double prime dot product with U divided by norm of alpha prime squared. Here is the proof. Well, first of all, note the following. The shape operator at evaluated at alpha prime is minus U prime. Why is that? Let's see the proof of this. Proof of the claim. This is something actually trivial. Just follows from the definition. Well, we know that by definition, well, not the definition, but we have seen this principle. Sorry, the shape operator at P along the vector V is nothing but the derivative of the unit tangent field at the point B along the vector V. Directional derivative of U at the point P along the vector V, or you take derivative of U at V and compute it in the direction V. Okay, and thus SP alpha prime, which is nothing but d dt minus U of alpha t. Okay, so derivative of so how would you take the derivative of U in this direction? You choose a curve whose derivative at that point is that vector. So here my V is alpha prime, so I just take that curve alpha derivative of this is just alpha prime. So it is this one. But what is this? This is by definition minus u prime t. Okay. Well, what we see from this, hence, u prime and alpha prime are collinear if and only if and only if s of alpha prime and alpha prime are collinear, because s of alpha prime is just minus u prime. But this means that, however, this means that alpha prime is just lambda times alpha prime, and thus alpha prime points in a principal direction. Why is it? Because principal directions are the eigenvalues of the operator S. Therefore, if alpha prime satisfies this, then alpha prime is an eigenvector. Therefore, it's a principal direction. And alpha is a curve whose derivative velocity vectors are in principal directions. Therefore, alpha is a uh, principal curve. Okay. All right. For the second part of the statement, well, if alpha is a principal curve, uh, alpha prime over alpha norm of alpha prime is a principal direction, because it's a unit vector, principal direction. Hence, if ki is the principal curvature, is the principal curvature in the direction of alpha prime over norm alpha prime, which is the principal direction, then we see this. The principal curvature along this principal direction is just ki times the principal direction. So ki, which is just alpha prime okay, we have this. But S is a linear operator, therefore this is just S of alpha prime dot product with alpha prime over this 1 over alpha norm alpha prime goes out, so we get square of this, or I can write it this way, and this finishes the proof. Okay, so this gives us a way of computing curvatures along principal curves. You just take second derivative, multiply with the unit normal field, and then divide by the length square of the velocity vector. Here is another lemma. Let alpha be a curve cut from a surface M in R3 by a plane. So I have a surface, and then we just cut that plane by a plane, and we obtain a curve. If the angle between M, the surface, and the plane by a plane, let me say P, is constant along the curve alpha, then alpha is a principal curve in M. Okay, so what does this mean? Uh, okay, so okay, let me do the proof, and then okay, I'll do the example later. First, let's see why this is the case, or maybe I can just explain on a figure. Suppose we have a sphere. When we cut this by a plane, sorry. So suppose we cut this by a plane like this, so we get a parallel. Uh, the angle between the plane and the surface, so okay, so maybe I should. Okay, it's at a point like this. The okay, this is M. This is the center of the sphere, let's say. The normal direction of the plane is like this. Normal direction. The normal direction to this to the sphere at this point is what? You just okay, so it's like this, I guess. So here at this point, for example, it's like this, the normal direction. At this point, it's like this, and you just take this curve and move around, and this direction, so uh, it points a little bit upward, uh, since I cut this with a plane parallel to the z-axis, let's say, uh, this vector changes as I move along alpha, but the angle between this vector and the z-axis is always constant. Okay, so this angle is always constant. Therefore, this parallel is an principal curve. Okay, actually, along any surface of revolution, parallels are principal curves. All right, let's see the proof of the lemma. Let u and v be unit normals to m and p respectively. So this is the normal to the plane, and this is the normal to the sphere u respectively. Uh, thus, v prime is 0 since p is a plane and uh, normal vector is constant, and thus and hence v is constant on p, therefore its derivative is 0. On the other hand, on the other hand, by the assumption the angle between u and v is constant, therefore this inner product is constant, because what is this inner product? Norm of u, norm of v. So let me write, this is norm of u times norm of v times the angle between the two, but these are just unit vectors and the angle is constant, so this is a constant by the assumption. Okay, well, take derivative with respect to t to get, what would you get? You get u prime dot v plus u dot v prime, and derivative of constant is 0. But we already know that this is 0, therefore we see that u prime dot v is 0. Hence u prime is always perpendicular to v at along the intersection of the surface with the plane, which is the curve alpha. Okay, well, this means in particular, in particular, u prime is normal, is normal or perpendicular. Let me write perpendicular to both the surface M and uh, uh, P. No, 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 no. Okay. U prime is perpendicular to V. Yes. No, I should write. That's not okay. Uh, we also know that since alpha is a unit speed curve in both M and P, alpha prime is normal, is perpendicular to both U and uh, V. Uh, well, U prime is okay, since U prime is a unit vector field, U prime is perpendicular to U also. So U prime is perpendicular to both U and V. Therefore, and alpha prime the same way, it follows that alpha prime and U prime are parallel, are collinear, because they are both perpendicular to two vector fields which are U and V. U and V. Okay, but this means that by the previous lemma, so the previous lemma says that a curve is principal if and only if U prime and alpha prime are collinear. Hence, by the previous lemma, uh, alpha is a principal curve. Okay. Of course, this is valid if uh, of course, implicitly, we assume that U and V are linearly independent, right? Because I made this argument. Here is, sorry, here is the vector U and here is the vector V. And we have two vectors which are perpendicular to both of them. One of them is alpha prime, the other one is U prime. So U prime is something like this, which is perpendicular to both of them. And alpha prime is another vector which is perpendicular to both of them. So I have this. Okay. Therefore, alpha and alpha prime are collinear. However, if u and v are not linearly independent, as in this picture, then this argument doesn't work. So we have to assume the other possibility also. We have to consider the other possibility. If u and v are dependent, linearly dependent, then of course, since they are both unit vectors, u is plus minus v, either v or minus v. By continuity, it is one of them for all, at all points. In particular, hence, u prime is equal to v prime plus minus v prime, but that is just zero because v is a constant vector field. This means that u prime is also zero. Well, in this case, of course, if u prime is zero, then alpha is clearly principal, because it means every direction is yeah, yeah. Okay. Uh, okay. More examples, maybe. Uh, uh, Let M be a surface of revolution of revolution. Then any parallel and any meridian curve is principal. Why is that? Let's see. So okay, so let me say this is the axis of rotation, and I have a curve like this, and we rotate this about this uh, you know axis, and let's say we get something like this. Something like this. And if I rotate this, I will get a surface like this. What's a parallel? Parallel is a curve. You just, if you, so to get a parallel, cut the surface by a plane having the rotation axis as its normal vector. It's normal. So, for example, uh, take a plane like this. Okay, you will get a curve like this. The normal to this plane is just, the rotation axis. Okay, so this is a parallel curve, and the angle between the surface and the vector v is constant in this case, because I just take this point and rotate it along the curve. Suppose the surface normal at this point is like this, the vector u. You just take this and rotate here. The vector v is like this, and this angle will be constant along alpha. So alpha is a parallel curve, and it is a what uh, principal curve in this case. What about a meridian? A meridian is a curve. A meridian is obtained by cutting the surface of revolution m by a plane containing the axis of revolution. Revolution axis. So if I just take a plane containing this line and cut the surface via that plane, I will get a meridian curve. So let me draw a meridian curve. A meridian curve will be, for example, this is a meridian curve. This is a meridian curve. Okay, so this is a meridian curve. Again, in this case, the normal vector and the angle between the surface will be constant. Okay. Yeah. In this case, it will be always 90 degrees actually. For example, consider this plane like this. So this is the meridian curve. Normal to this surface at this point points in this direction, but normal to the plane will point in the direction above the screen. Therefore, it will be 90 degrees. So in this case, in this case, the angle along uh, the meridian uh, along the meridian between u and v is pi over 2. Okay, it's always pi over 2. Okay, Here is another definition. Uh, Directions tangent to M in which the normal vector, the normal curvature, I'm sorry, is 0 are called asymptotic directions. Okay, so a tangent vector V is asymptotic if the normal curvature, which is SV dot V is 0. Okay. Okay. Asymptotic directions uh, are, of course, the directions where the curvature is normal curvature is 0. Okay. Well, it is not clear that we have such directions all the time. The lemma here just explains this. So let P be a point on a surface in R3. Be a point. Then we have the following. If the Gaussian curvature is positive, then there are no asymptotic directions at P. And the second uh, part of the lemma is this. If this is negative, then there are exactly two asymptotic directions at P, and they are bisected by the principal directions. At uh, directions at angle, let's say angle nu such that this angle is something uh, special. It is tangent squared nu is minus kappa k1 divided by k1 over k2. And the third condition is that if the Gaussian curvature is 0, then every direction is asymptotic uh, if P is a planar point. Otherwise, there is exactly one principal direction, yeah, there's exactly one asymptotic direction, and it is also principal. So that asymptotic direction is also principal. Uh, Proof. Well, recall Euler's formula for principal curvatures. Remember, Euler's formula is this: k1p cosine squared nu plus k2p sine squared nu, where, remember, we have this. At the tangent space to the surface, we have principal directions, let's say E1 and E2, and any other vector, uh, let's say, which makes angle with E1 this much, then the principal curvature along the vector U is given by this formula. Now, uh, if this is positive, Gaussian curvature positive, well, Gaussian curvature is just, we know that this is K1 times K2. So if this is positive, then of course K1 and K2 have the same sign. So they are both positive or they are both negative, and thus, and they are non-zero, of course, and thus Ku is never zero, is never zero. Either it's always positive or either it's always negative. So there is no principal direction. There is no direction in which the normal curvature becomes zero. All right. If Kp is negative, then of course K1 times K2 is negative. So one of them is positive, the other one is negative. But then just setting this to zero, then uh, setting this to zero, we see that uh, then for a vector u with angle nu satisfying what? I just equate this Euler's formula 0 to 0, so we get what? Tangent squared nu, tangent squared nu is okay. Tangent is just sine over cosine, so it is minus k1 divided k2p. But they have the opposite signs, therefore this is positive, and therefore uh, uh, such and thus uh, this implies uh, such nu exist. Therefore we have two directions in which one of them is the positive square root, the other one is negative square. So I have two angles, and along those angles, the normal curvatures are 0. Okay, and what happens is this. In this case, so this angles, one of them is the positive, this angles, one of them is, okay, so tangent mu1 is square root of minus k1 over k2, and tangent, this is the second, let's say, angle, this is minus k1 over k2. So our angles are like this. One of them is let's say this one, u1, the other one is this one, u2, and our principal directions are like this. uh, yeah, our principal directions are like this. Therefore these two okay, directions, these two vectors are bisected by e1 and e2. Okay, that's the uh, content of the second part of the theorem. The third one, now assume Gaussian curvature equal to 0. Well, uh, then either k1 and k2 are 0, which means uh, p is a planar point, and in this case every direction is asymptotic, because normal curvature is 0 for all vectors, or one of them is 0, or one of them is 0, or only one of k1 or k2 is 0. Well, say k1 is 0, then our curvature becomes what? K2 times sine squared nu, right? Yes. So when this is 0 and ku is 0, exactly if nu is 0 or pi. So there is only, and this implies the the asymptotic direction is just uh, where the angle is 0 or pi, so this is E1, okay? Hence, the asymptotic direction is the principal direction. Therefore, in this case, the two directions coincide. And this finishes the proof. Okay. There is one example. Let me draw this example. So we have a part of a for example, a torus. Take this, and let's say I cut the surface okay, like this. So this is the plane P. This is, let's say, our surface. In this case, it's a torus. At such a point, my curves, when I cut the surface with this plane, I get two curves through this point. One of them is this, the other one is this. So two circles. And okay, so this is my, let's say, point P, and my asymptotic directions are these. One of them is this direction and the other one is this direction. Let's say A1 and A2. Asymptotic directions. What are the principal directions or principal curves? Principal curves are these. In this case, one of them is this curve. Okay. Well, maybe I shouldn't draw or choose a different color. Let's see. Yes. So one of them is this and the other one is this. So these are the principal directions or principal curves, and these red ones are the asymptotic curves. Okay. Now let me give the definition of asymptotic curve. We defined asymptotic direction. Right? Yeah, we defined asymptotic direction, but we haven't defined asymptotic curve. So a regular curve, alpha in M, which is a surface in R3, is an asymptotic curve provided its velocity alpha prime always uh, points in an asymptotic direction. Thus, alpha is asymptotic if and only if the normal curvature, which is just shape operator evaluated at alpha prime dot alpha prime is 0. Okay. Well, since we already know that, uh, remark, maybe I should, since we know that S of alpha prime is just minus U prime, alpha is asymptotic if U prime that alpha prime is 0. Okay. Moreover, in this case, uh, however, in this case, okay, maybe I should say, on the other hand, alpha is a curve in the surface, and thus the tangent vector to alpha lies in the tangent space to M. Therefore, this tangent vector should be normal to U. So, taking derivative, we get what? Uh, Alpha prime U prime plus alpha double prime U is equal to 0. But I know that alpha prime U prime is 0 for an asymptotic curve. So this is already 0. Therefore, we see that the acceleration of alpha is always perpendicular to U. So acceleration vector lies in the surface. Okay, this will have important consequences which will be covered in the next lecture. So let me stop for today.